So, if you've been following my work for the past few years, you might be knowing what's going on, but in case you haven't, I'll try to summarize in a minute or so. So the basic idea is to take regular kernel code and run it in an unprivileged domain. Now this is actually not a new idea. You know, it's been called virtualization, it's been called microkernels, probably some other names too. But my new angle here is the idea that we don't need a heavyweight virtualization stack, we don't need multiple different layers of schedulers, we don't need to implement locks on many different layers, we don't need a special kernel for a microkernel, we can all do this in a regular Unix process. And the key word here is, of course, unmodified code, so just take kernel code and it will automatically work in user space. This is based on the assumption that privileged instructions don't exist, and in most cases they actually don't. And in addition to code, it's possible to take a kernel module binary and just use it as a library in a user space program. This approach, I've already written a few different papers, has been successful with file systems and networking, and there it was noticed that on the host, which is the machine you're actually running the virtual kernel on, you only require minimal support from the host system, from the host kernel, and most of the time just a regular POSIX kernel is enough. And this talk is about the extension of the same idea, like file system networking. The next logical step is device drivers. So my talk outline, first I'll give some motivation to the subject to see if this is actually a useful topic, a useful problem to solve, or if I'm just doing this for hack value. I'll introduce concepts a bit more carefully to make sure you're up to date on what I'll be talking about. Then I will take a moment to explain what a driver proxy is. And the driver proxy is not what I'm doing. When I was doing this for file systems, kernel file systems, people often came to me and, yeah, I like your idea, but how is this different from Fuse? Well, a Fuse is a driver proxy. Here I'm talking about an actual method, so kind of as the analogy to file systems, the actual method is the block layout, the namespace layout, and how those map to disk, not the problem of having an implementation in user space. Then I'll talk about pseudo devices, I'll talk about USB hardware drivers, and then I'll talk a bit about how to specify device configurations. This is mostly a side step which I would have hoped NetBSD would have solved for me, but NetBSD isn't modular enough yet, so I have to kind of take side steps into that area too. And actually this is interesting in the sense that rump is something, or I have a theory that if you implement a modular kernel correctly, rump, or the idea of being able to run your kernel code in user space is something which will just fall out of that correct implementation. And finally I'll offer some conclusions if there are any. So, how many different use cases do we have for running kernel code in user space? Well, the obvious ones and the kind of itch I started scratching is development and testing. Now, you might think that, okay, there are virtual machines, there are emulators, but if you haven't tried driver development in a user space process, well, that's like way easier and way simpler. And for testing is brilliant because you can test different kernel features, you can run a set of regression tests, and if you happen to have a kernel regression and your test or kind of your kernel code crashes, no, you just get a core dump, you can continue testing, so it doesn't actually affect your test suite. Then in the end, when you run your 10,000 tests, then you get a report that 9,999 were successful and one failed with a core dump, which would have been a kernel panic. Now, if you would use an emulator for this, of course, an emulator takes a long time to bootstrap. Running tests is not as simple. And of course, also, if you want to do fault injection, this is good, because then you can easily, like, if the expected outcome of the test is a crash, and you have, let's say, 100 of those, you want to test that, okay, these invariant tests are still valid, so they don't cause silent corruption. If you inject faults, then you immediately notice that, okay, now the faults are correctly detected. For open source, better bug reports from users. Now, if someone reports a bug, okay, I do this, then my kernel crashes, and it depends on some special hardware or some special environment that you can't easily reproduce yourself. You can ask the user, okay, run this simple program and try if you can repeat the problem in this program, and then you can debug a program, a simple application. And of course, asking an average user to execute a few GDB commands in a simple program is way more likely than they would start setting up a kernel debugging environment and all this thing which we know is kind of hard. Then, since we're talking about user space, we can use kernel drivers in a host or operating system independent fashion. Well, this is true to some extent. There are some buts and some cases where this doesn't apply. But for example, I very often run, well, actually I do run on my workstation the NetBSD 5 release branch, and then I run device drivers from current in user space process and do development that way and take advantage of new features and so forth. Then security. Security is a funny issue. It applies especially for file systems, but also for device drivers. See, when you think of a normal kernel, it's very well bulletproofed from the sense of what applications do. So, you know, system calls are very carefully all the arguments are validated and so forth. But when you take an average file system driver or a device driver, it really doesn't validate arguments that much. So in the case of a file system, an evil file system image can very easily cause a crash or even an exploit. And I never ever anymore mount untrusted file systems with the kernel driver because the risk of exploit is really real. And then of course you can extend for hardware this concept to, let's say, evil devices. Of course it's easier to manufacture an evil file system image than it is to manufacture an evil, let's say, USB stick, but that might still be a valid concern for someone. And then finally, why would you want to run kernel code in user space? Well, for improved performance. And no, this is not actually a joke. So, for example, if you read the Mach papers, the reason they wanted to run device drivers in user space initially was so that they could get more performance out of their networking stack. Of course, their networking stack was already running in user space, so they could. They could avoid extra data copies that way. Now, of course, if we extend this idea, we can have very specialized versions of the networking stack when it's in a user space process tuned specifically for some application, and then when you add a networking device driver to that, you can get very, very high tuned performance. So the basic architecture of RUMP is like this. You have a single process where you have kind of an application portion, which is the program logic, whatever you want your program to do. and it uses kernel code kind of like a library. So the regular interface the application can use to access the kernel is the system calls interface, but instead of like the call is the same, but instead of trapping into the host kernel, it makes a function call into the rump kernel. And in the rump kernel, you, depending on your configuration, you have different components. Like let's say this one has networking and file systems and device drivers. If you're just doing networking, you maybe don't need file systems at all. Yes, it is possible to run a kernel without VFS. I do it all the time. And then you have support routines like threading and memory allocation. Well, in the rump module, threading is actually implemented in the host. So typically a rump kernel thread would be a host pthread. And since this code is all in the kernel namespace, we don't have direct access to any functions in the userland namespace. So there's kind of this extra abstraction layer which is kind of like a hypervisor which the rump kernel uses to request services from the host. For example, the memory allocator requests a big block of memory from the host through the rump user interface, and then does what a memory allocator normally does. When you create a thread, it goes through here and then ends up here, and then like this fine graphic shows there are no direct calls from the rump kernel to the host. And this, well, you do need to implement this extra layer, but actually it's also a good thing, since now you have a very good idea of what your host needs to support to be able to support a rump kernel. This is some, well, I didn't count it, but let's say 40 different interfaces, things like open and read and write. And well, of course, it fully doesn't quantify what is necessary, since for open you can open some random device which might not be present on your host. Let's say if your host is NetBSD, it might be present. If your host is Linux, it might not be present, or it might be present and behave a bit differently. So kind of independent, but there are gotchas. And an important thing to understand is here that each rump kernel, which is always one process, you can have one of them, you can have 0 of them, you can have 10,000 of them running on one machine. It always has its own namespace for everything. So the file system namespace is unique to that rump kernel. The file descriptor namespace is unique. The device namespace is unique. So you just kind of, here's an example. So you open the dev null device in a rump kernel, then you can do the rump write system call to it, and it does the expected thing, which is nothing. But then if you try to use the host write system call for the same file descriptor, you get undefined behavior, because let's say this might return file descriptor 5, and that might already be used by the host in your application. And like I already mentioned, the rump kernel is built from different components: networking, device drivers, file systems, so forth. So typically, for example, in the context of this talk, one device driver is one component. So you have USB mass memory, that is one component. You have USB printer, that is another component. Then I promised I'll talk about a file or a device driver proxy. So this is actually something I wrote back in 2007, and then I forgot about it, and then when I was doing this work last December, I remembered, aha, I can actually use that to my advantage. So I'll explain, or I'll have a graph on the next slide, but I'll just quickly explain what this is. So if you're familiar with puffs, this is exactly like puffs, except for providing a method for implementing a file system in user space. You can implement a character or block device. And you just register an entry to the kernel, and then after that all requests go into, let's say, major number 258, are directed to the user space server where they can be handled, and then it passes the results back. And like puffs, but doing this for device drivers is a lot simpler than doing it for a file system. Okay, so here's the graph I promised. So we can run device drivers with RUMP in kind of two different modes. One is kind of a server or proxy mode, where you have your application and your application makes regular system calls, so it's completely ignorant of the fact that the actual server handling the system calls is in user space instead of the kernel. So application makes a system call, let's say it's a read to a device. It's passed on to the device switch and the pod portion in the kernel, then it's passed to user space, and in user space it's passed to the RUMP kernel where the actual kernel device driver handles the request. And if the kernel device driver needs some resources, let's say allocate memory or something, then it hooks back to the kernel. And the other option is that RUMP device drivers are used like an application library with explicit system calls, like we saw a few slides earlier where we opened DevNull and then wrote to it. Now, the difference between these is that this is transparent to any application, but it requires some privileges to start the server. So and it also, of course, requires a kernel implementation, so this is not a part of POSIX. And this, on the other hand, you need an explicit application, but it can be totally or mostly unprivileged. It depends on what you need to do here. If you need to access a certain host on a certain device node on the host, then you might need special permissions to access it. But this portion is completely unprivileged, and this is excellent, for example, for writing regression tests and basic development. So device drivers can generally be divided into two classes in BSD. We have pseudo devices, which, well, they aren't really device drivers at all, but they are just some random collection of code, and well, they run in user space pretty well. They are typically accessed through a device node in /dev, and here's a few examples of which pseudo devices I support now. So the Berkeley packet filter, the cryptographic disk driver, the LVM device mapper, write frame, the NetSMB Samba pseudo device, which is required for the Samba file system client, and so forth. And then, as opposed to pseudo devices which don't have any hardware, we have real devices which actually drive some hardware devices. And these are sometimes accessed through a dev node, like for example in the case of a SCSI mass memory device driver. Sometimes they're not, let's say for example in the case of a Ethernet device driver. To drive real devices, we of course need some method of accessing the hardware. I'll get to that soon. And currently I have support for USB devices. I have some plans to extend this, but I haven't gotten around to it yet. So device access for this slide means access to /dev. So, as I mentioned previously, a RUMP kernel has its own namespace for everything. So if you have a dev node on the host operating system, that doesn't mean you have a dev node inside your RUMP kernel file system namespace. Nor does it mean that a device node on the host has the same major or minor number as the one in a RUMP kernel. So how I do this? Well, there's no support for DevFS in NetBSD yet, but when a component is added to or configured in a rump kernel, I just manually create the necessary device node. For example, for a SCSI disk component, I have code which just makes a few device nodes. For a printer, it makes the printer device nodes inside the rump kernel and so forth. And usually the root file system of a rump kernel is non-persistent, so I can just pick any numbers when I start the kernel, which means run the program, and then if I have a different configuration in another kernel, it might pick the same or different major numbers, but that doesn't matter because they're completely dynamic. And after, of course, the devices exist in the rump kernel, we can use them. Like in this short example, I show how to access the BPF device. So let's say we have a rump kernel with the BPF component, some networking component. And we can open the BPF device as normal, so we just call rumps is open for dev BPF. When the BPF component is initialized, it automatically created this device so we can open it. Then for BPF we need to configure it, so since this is the same as the kernel BPF driver, we do it the same way as you would for the kernel BPF driver. So you use the IF request structure, and then you just tell it, okay, we want to process packets for interface named ifname, and we use ioctl to set that operation. Then we have a simple BPF program which just returns all packets. And once again, we use ioctl to set that program for that instance of BPF. And after that is done, we can basically start reading packets from BPF. So all traffic which goes through the rump kernel, you get as BPF packets. And of course, what you get out of BPF is what you get out of there normally. So it has the BPF header and, well, I can't remember what it has, but the BPF header and then the payload follows. And of course you could also set, this is the maximum amount of payload I want to receive, and you could basically load up any program, but this is just for testing, so that was a simple case. Here's an example of what you can do with the cryptographic disk driver, which is of course normally used to protect disks on mobile media such as laptops or so forth, or encrypt them. So well, first of all, what I want to do here is write an application which encrypts and decrypts, or can encrypt and decrypt some file on the host. So what I need to do first is give the rump kernel some way to access a file on the host. And by default, of course, the rump kernel uses internal namespace. But for example, similar to VMware hostfs, I have something called etfs, which I can use to say that, okay, if this file name is accessed, it's actually not inside the rump kernel, then you actually have to access a file on the host. So let's say I configure file.image on the host to be accessible in the rump kernel with some name, let's say encrypt. Then I configure CGD for that, or configure this cryptographic disk driver to access this file, and after that I can simply read or write, well, this is shortened, so this should be /dev/cgd0a. But after that, when I read or write the cryptographic disk driver device node, I actually encrypt or decrypt the actual file on the host. Now, well, of course, we already have PGP and things like this, so this is maybe not that necessary, but the cool thing we can do with this is what Roland, the author of CGD, thought about is we can build an application. Well, since CGD is the same CGD used in the kernel, so we can build an application which is run as part of the build process, and you can build encrypted disk images using this. So you can ship, let's say, CDs with an encrypted image on them, and when you bootstrap the CD with a regular NetBSD kernel, you can still read and write it because it's actually the same code which is doing the encryption and decryption in the application or on a real kernel. So this is just something you can do. So then moving from device drivers to actual hardware devices. So like I mentioned earlier, a thing necessary to do is be able to access the hardware. That's the first thing a device driver needs to do, and this requires some special privileges or some special method to be available for a user space process. Of course, if any user space process could access any devices, it would be kind of difficult to implement a secure system. So in some cases, things are really or have been made really simple for us. They are already available. For USB, the USB generic device driver is available, which provides generic access to a USB device. For SCSI, we have the SCSI UK or unknown device driver. I have actually not investigated that very closely, but it might be possible to use it or to drive kernel SCSI drivers in user space. And other times things are a bit more complicated, like let's say with PCI device drivers which want to do DMA, and well, there's a few approaches to this which I listed in the paper, but one approach is to just ignore the problem. So just let a user space process program a DMA controller. Now, of course, if you want security out of your system, that's out of the question if you're able to write any physical memory address. But if you want to do development, it's kind of like let's say 99% solution. So as long as you're very careful about programming the DMA controller, you can still easily do device driver development in user space. And before we go more deeper into device or USB device drivers, let's look at a typical device tree for a moment. Now, this is of course not from a real kernel. This is from a RAM kernel, so it's kind of limited, but it contains several important things. So at the root of every device tree is root, which is not very surprising. Typically you have some pseudo bus called main bus attaching to the root, and in this example I have two different USB host controllers. So I have USB host controller 0 and USB host controller 1, and these correspond to the host device nodes UGen 0 and UGen 1. On this side, every host controller comes with a root hub, which is attached directly to the host controller, and on the root hub, well, whatever is present is present. So in this case, we have a SCSI disk and a CD drive, and we have several intermediate layers of different device drivers, all of which we need to run in user space for this whole stack to be runnable in user space. Then on the other side we have another root hub, and then we have again a kind of pseudo layer, the USB human human interaction device, or whatever it stands for. And then we have a mouse driver attached to that, and then we have kind of the mouse abstraction layer used in NetBSD, which is WS mouse. So these are kind of two different driver stacks we'll look more closely into. So what's special about USB is that the host controller controls all traffic on the bus. So when each device driver wants to access a device, instead of accessing the driver directly, it sends a request to the host controller. Then the host controller takes care of the actual device access. So what this means for user space is that, like, all the hard stuff, all the interrupts, all the DMA, all that hardware specific stuff is actually hidden in the host controller device driver. And then if we look at this part, if we're just interested in kind of running the actual device drivers and not the host controller driver, we can get away with doing an implementation of the host controller driver, which translates requests so that it talks to the generic driver. And even this turns out to be fairly simple, since what the generic device or UGen eats is normal USB requests. So we get a request from some device driver, then we basically only have to write it to the UGen device on the host, and then that's it. Simple. Of course there are details, and then it's maybe not that simple, but the basic idea is very simple. So what's currently supported with this method? Well, basically all the USB hardware I have access to. So mass memory, including SCSI and ATAPI ones, and including drives and CDs. Then there's some support, or there is support for serial adapters and USB modems. They're basically the same thing. There's some bug somewhere in the code which causes them to lose characters every now and then, and I haven't managed to investigate closely into it yet, but they basically work to, what's special about them is they require kernel TTY layer support in RAM, so that's just code again which runs in user space easily. There's printer support, in case you for some reason want to have your printer driver in user space. There's support for mice and keyboards, which is fun. You can write all sorts of fun applications where you can move a mouse cursor around the screen, which is, I'm sure, very useful. They require the WS console support. And then what this means, there's some support for USB wireless network interfaces. Well, that means that I had access to a USB or a USB network interface card for a short time, and during the period I had access to that card, I didn't have access to a wireless network, so I didn't actually get to test. You can run traffic through it, but you can configure it and probe it correctly. If someone wants to lend me one, I'd be more than happy to finish that work. So another example, this time with a USB SCSI device, we want to mount a file system from that SCSI device. We set up the argument structure for the mount system call, we create the mount point, and then simply run the mount command. So then there's a question, what would happen if instead of rump sysmount we would actually use the mount system call? Well, of course, then the file system would be mounted on the host, and then additionally SD0E from the host would be used, which might or might not be present, and which definitely will not be the same device as the one probed as SD0 in the rump kernel. And of course, this also demands that your rump kernel has a VFS component, and it has the FAT file system component, so you can actually mount the correct file system. Another example which demonstrates the dual nature between the host and rump is printing a file. So we open a PostScript file on a host, then we open the printer device where the driver is in the rump kernel, then we read from the host and write to the printer. And you notice this is a host system call, this is a rump system call. Read from one place and write to the place where the driver is. Then when we're finished, we can't read anymore, we close all the scriptures and then we're done. Then at least what happened when I tested it, the printer started making noises and then some paper came out. So apparently it worked.
I have a question about the previous example. So what happens if you mount the same system twice? One in...
You mean this one?
Yeah.
Same system twice?
Yeah, like so you can mount it in a rump kernel and you can mount it in the real kernel.
Yeah, but the same device isn't present in both. So see, the namespaces are different. So SD0E inside the rump kernel is not the same SD0 as on the host kernel. So you can't mount them both at the same time. Or
can you have the same device present in both kernels?
No, not currently. Because you have one driver driving one device. So if you could have two drivers driving one device, they would of course collide even earlier than in the file system. So it's kind of the same thing that if you have two keyboards and try to type onto one machine, like you have two keyboards connected to one machine, and if you're typing, then obviously collisions happen. So. Yeah. So, autoconfig glue. As I mentioned in the beginning, this is kind of stuff which I would have liked to avoid doing, but NetBSD support for modular or kernel modules with device drivers is not far along, so that I could avoid doing it. I actually, my first intention was, let's borrow some code from FreeBSD. They probably have done this. But then I noticed that the config utility and how device auto-configuration is done is so different in the two systems that it was hopeless. So I quickly gave up and then decided just to do something on my own. So if you're familiar how this works in NetBSD currently is when you build a kernel, you have a kernel configuration file, you feed it to the config utility, and then the config utility, in addition to building tables which are used by the device auto configuration, it does everything. So it creates kernel make files, it creates build directories, it creates everything, like lots of stuff we're not interested in when we want to just support one device driver. So this is very much targeted for a monolithic kernel, and what few device drivers we support currently as modules use very ad hoc methods. The tables produced by config are, let's say, difficult to write by hand and even more difficult to read by hand. I have pretty good experience in that because I kind of wrote plenty of them by hand before I started patching config to do the hard work for me. So, of course, somewhere in between writing them by hand and patching config, I also realized that I could actually just write a config file for a monolithic kernel, then copy-paste the necessary information, but it's still a lot of work and difficult to configure. And this, like I said, more related to modular kernels than the basic idea of rump, but since those are kind of partly related concepts anyway, we get some synergy benefits. So what I did is I introduced two additional experimental keywords to config input on NetBSD. One is IOConf, which instructs config to produce just the necessary tables for device auto configuration, which tell where this device can attach and how it attaches and so forth. And then, since if you remember the example device tree I showed earlier, or config assumes that all configuration files start from root. So if you don't have a path from root to a certain device, that device is orphaned and will not be included in the configuration. Now, when we are talking about fine-grained modules and components, we don't want to have the specification from root to each device every time. We just want to have a certain bit from the device tree. And sudo root, what it does is just creates a fake node which devices can attach to. So here's an example of what it looks like for a mouse configuration. So we have IOConf USB mouse, then we have a sudo root for the USB hub. So here's the entire device tree starting from root. We have main bus, the host controller, and the root hub associated with the host controller. And these are not included in the device configuration produced by this device configuration. They just exist conceptually. And sudo root just tells that, okay, a hub exists but does not output anything for it. And then we can actually attach the necessary devices. We attach the human interface device, then we attach the mouse to it, and then we have the WS mouse. Of course, this is still not as fine-grained as I'd want, since, for example, if you have a different component for a keyboard, you'd want the human interface device attachment to be independent of the mouse attachment. So I'd want to have another component which has only this layer, and then this CRUD is in this layer, or even maybe WS mouse in a separate layer. So, conclusions. Well, the aim of the work was to run unmodified kernel device drivers in a user space process. That is certainly possible. I have done it, I do it all the time now. What's good about this unprivileged process cannot crash the host kernel, except if there are bugs in the host. I've noticed there are several, or at least were several bugs in the USB generic driver. So if you happen to unplug a USB device at the wrong time, or let's say in the case of U3G or U3G UMTS sticks, where they actually configure themselves as one device first, then when you vomit some information to them, they detach and reconfigure themselves and attach as another device. That had some race conditions, so when they detached, some bad things happened in UGen and so forth. But theoretically, unprivileged processes should not be able to crash a normal host. So this is a definite advantage of the method if you want to use it for driver development. Your drivers are not limited to a single host. Mostly, like I said earlier, I run NetBSD 5 on my workstation. I use current drivers. Use cases not limited just to driver development. You can build all sorts of applications using this. You can reuse your kernel code. So one of the points is to show that if you already have a kernel space implementation, it's not necessary to do a separate user space implementation of the same functionality. If you implement your operating system correctly, you can just use the kernel driver in user space as is, so the kernel driver can shine on. Future directions with this work: support even more hardware, support more devices, even maybe look at the difficult ones such as PCI, improve config more so that I can auto-generate more stuff from information already there. I hate typing, I like other stuff much more. Some of the advanced or the features for config I showed, I could use NetBSD kernel modules to use them. And then one problem I currently have is component auto-dependencies. So when I talked about or showed the USB mouse configuration a while ago, I said I could break it down into more fine-grained components, but now the component dependencies are not automatically managed, so handling them becomes very, very tedious when you have, let's say, 50 of them you need for a single rump kernel. It used to be simple with file systems. You only needed the base rump kernel component and the file system driver, but then things started growing, and now you might need, I don't know, 10 or 15 of them. So if they could somehow automatically load each other when they are necessary, that would be great. And all the work presented here is available in source and binary form from NetBSD current, and of course runs on any host. Maybe. Okay, thank you. Questions?
I have multiple processes that have to have the same device. There are mechanism to share between those processes or to share the whole ROM kernel.
Yeah, so the question was that if you have multiple processes which need to share the same device, is there a mechanism to do the sharing? Well, I've written some initial code so that the rump system calls could be used over a socket. So you could have kind of one process where you have the actual driver, and then if you want to use it from that one, it's okay, you just do normal function calls. And then if you have another process you need to use the same driver, you do system calls, but they're proxied over a socket. So it kind of exists, but it's still not production ready. It works in some cases, but that's one method you could use. Of course, it's quite slow to make system calls over a socket, but yeah, that's the one that comes to mind right now.
How can the implementation accesses your devices? I mean, is backspace function usable to current your apps, or you are using
Yeah, so the question was about generic access to device drivers, and is it possible currently to use bus space and bus DMA present in NetBSD? The short answer is well, for bus space, no. For bus DMA, sort of. Like I said, this USB work was easy because everything is handled by the host controller. So it uses the USB-DI, which is probably USB device interface or something like that, and all USB drivers talk directly to the host controller. The only thing that they do is they reserve DMA safe memory using bus DMA. But of course, since we know that the host controller is implemented in user space and it doesn't really do DMA, we can just malloc DMA safe memory. And as for generic bus DMA support, well, that is something I want to look into in the future, but not supported currently.